In this video, we're going to look at another example of moments and centroids. Consider two masses, M1 and M2, attached to a rod of negligible mass on opposite sides of a lever at distances D1 and D2 from the lever. The rod will balance provided M1 D1 is equal to M2 D2. For example, think of a smaller mass balancing a larger mass by sitting farther away from the lever. Here's a smaller mass, M2, and here's a larger mass, M1. So the balance happens when M1 D1, the product of mass times distance, is equal to M2 D2. So because the M2 is a smaller mass, then it has to sit farther away to balance the equation. So the rod will balance if M1 D1 is equal to M2 D2. All right, so now consider a system of n masses, M1, M2, Mn, at positions x1, x2, all the way to xn, on the x-axis with center of mass at x bar. Our goal is to find the center of mass, to develop an equation for finding the center of mass. So let's first find a moment about x equals x bar, about the center of mass. This is equal to the distance of the first object, the first mass from x bar, so x1 minus x bar, times the mass of the first object, plus x2 minus x bar times m2, all the way to xn minus x bar times mn. And of course, we're just adding up these moments, mass times distance. We can write this in summation notation. The moment about x equals x bar is equal to summation k goes from 1 to n xk minus x bar times mk. So we're looking at a product of the moments. This is the distance of the kth mass from the center of mass x bar, and this is the mass of the kth object. Now, the center of mass of this system of n masses is a location x bar such that the total moment of the n masses about x bar is 0. So the total moment, m x equals x bar, is equal to summation k equals 1 to n xk minus x bar times mk is equal to 0. Now, splitting up the summations, we obtain summation k equals 1 to n mk xk, product of mass times distance, is equal to k goes from 1 to n mk x bar. All right, so what we obtain is summation k goes from 1 to n x bar mk is equal to summation k equals 1 to n mk xk. Now, k is a subscript variable. X bar is a constant. It can pass right through the summation. So we can solve for x bar. We get x bar is equal to summation k goes from 1 to n mk xk, product of mass times distance, divided by sum of the masses. Summation mk k goes from 1 to n. So x bar, the center of mass x bar of the system, is the moment about x equals 0 divided by the total mass. So the moment about x equals 0, this numerator is this part here, summation mk xk. The total mass, the denominator, is this part here, summation mk. So let's extend the definition of the moments to two-dimensional xy plane. Consider a system of n masses, m1, m2, all the way to mn, at positions x1, y1, x2, y2, and xn, yn in the xy plane. By analogy to the 1D case, the one-dimensional case in the x-axis, we obtain the moment about the x-axis is summation mi yi. I equals 1 to n. The moment about the y-axis is the product of mass times distance. But the distance is a distance to the y-axis, and the distance to the y-axis is measured by the x-coordinate. I equals 1 to n mi xi. And mass is summation mi, I equals 1 to n. That's the sum of the masses of the system. So a moment with respect to the x-axis measures the tendency of system of masses to rotate about the x-axis. My, the total moment about the y-axis, measures the tendency of the system of masses to rotate about the y-axis. All right, so here we have a diagram. We have these four masses at different locations in xy plane, and we're going to now generalize it to the n-dimensional case. So let's write down these formulas. X bar is equal to my divided by the mass. Y bar is equal to mx divided by the mass. And the mass of the entire system is simply the sum of the individual masses of these objects. I equals 1 to n mi. So x bar is equal to, the moment with respect to the y-axis is summation mi xi, the moment with respect to y-axis, divided by total mass, that's summation mi, I equals 1 to n. Y bar is equal to summation mi yi, I equals 1 to n, divide by summation mi, I equals 1 to n. All right, so now let's find the moments and center of mass of four objects with masses m1 equals 2 kilograms, m2 is equal to 1 kilogram, m3 is equal to 4 kilograms, m4 equals 10 kilograms, at points in xy plane, 1, 2, negative 1, 3, 3, 6, negative 4, negative 8. So those are just the positions in the xy plane, just like the diagram we had here. So we got four masses at different points in xy plane, and we would like to find the center of mass of this system of four masses. All right, so let's apply the formula. The mass formula, that's easy. Mass is equal to summation I equals 1 to 4, because there are four objects. Mi, that's equal to m1 plus m2 plus m3 plus m4. Summing up the masses. So we get 2 plus 1 plus 4 plus 10. Add them up, we get 17, say, kilograms, units of mass. The moment with respect to the y-axis is summation I equals 1 to 4 mi times the distance to the y-axis, which is measured by the x-coordinate, mi xi. That's going to be m1 x1 plus m2 x2 when I equals 2, plus m3 x3 when I equals 3, plus m4 x4. So the moment with respect to the y-axis is equal to 2 times 1 plus 1 times negative 1 plus 4 times 3 plus 10 times negative 4. This 10, for example, is the m4, the mass of the fourth object, which is 10 kilograms. And this negative 4 is basically the x4, the x-coordinate of the mass, which the x-coordinate of m4, which is negative 4. Now add these all up, and we get my, the moment with respect to the y-axis, is minus 27. Now mx. Mx is equal to summation mi yi. The moment about the x-axis is a product of mass times distance, and the distance to the x-axis is measured by the y-coordinate. So we get 2 times 2 plus 1 times 3 plus 4 times 6 plus 10 times negative 8. So 10 represents the mass of the fourth object, m4, which is 10 kilograms, and minus 8 represents the y-coordinate in the xy plane. And that's the distance of mass 4 from the x-axis, which is minus 8. Add these all up, and we get the total moment about the x-axis. We get mx is equal to minus 49. Now we can calculate the centroid. X bar is equal to my, the moment about the y-axis, divided by m. This is equal to, well, my is just minus 27. We calculated that, minus 27, and m is the sum of all the masses, that's 17 kilograms. If we decimalize this, we're going to get negative 1.59. And y bar is equal to moment about the x-axis divided by the mass. And the moment about the x-axis is minus 49. Divided by the total mass of the system is 17. If we decimalize this, we're going to get minus 2.88. So we have found the centroid of the system, x bar and y bar. All right, thanks.